Hey guys, I'm John and welcome to Respect Your Intellect. What's the difference between Newton's law of universal gravitation and Einstein's theory of general relativity? Why does Einstein's general relativity talk about gravity so much but doesn't actually have gravity in its name? Was Newton wrong and Einstein right? Those are some of the things we'll be talking about in this video. Don't forget to hit the like and subscribe buttons, and let's get started. In order to establish the main differences between Newton's law of universal gravitation and Einstein's theory of general relativity, let's start with the difference between a law and a theory in science. A law is an explanation of what happens, while a theory is an explanation of why something happens. In other words, a scientific law is the description of an observed phenomenon. It doesn't try to explain why the phenomenon exists or what causes it. The explanation of a phenomenon is the scientific theory. It's a very common misconception from non-scientists that theories eventually become laws, but they can't. They describe and explain very different things and each have their own separate concerns. The full misconception from non-scientists is that as science finds more evidence for something, the hypotheses get upgraded to theories, and if the theories are then found to be correct, they get upgraded to laws. In reality, neither of them can be turned into another because they have nothing in common except that they're all part of the scientific method. Hypotheses are limited explanations of a phenomenon, theories are in-depth explanations of a phenomenon, and laws are statements about an observed phenomenon or a unifying concept. Hypotheses just require enough evidence to respect the burden of proof and show that the hypothesis has merit. Laws and theories are always supported by a large body of empirical, in other words verifiable, evidence. The last thing to mention here are facts. Facts are simple and basic observations that have been shown to be true. For example, my house has a garage is considered to be a fact because it's a statement that can easily be proven to be true. Both theories and laws are generally considered to be facts because of the countless amount of pieces of evidence that support them being true. Gravity is actually one of the best examples of the difference between laws and theories. Newton came up with the law of universal gravitation, which describes the effects of gravity, but it makes no attempt at all to explain how gravity works fundamentally, what it is, or why it exists. Einstein's theory of general relativity, on the other hand, is a theory that implicates much more than just gravity, which we'll get into in just a moment. But it does include the effects of gravity on the fabric of space. So Einstein gave us more information as to why gravity works the way it does, and it allows us to account for many other phenomena that Newton's law didn't make any attempt to address. Newton's law and Einstein's theory still both work today. We can still use Newton's law to land robots on Mars or calculate estimates that are still pretty accurate. This is ideal when the goal is to keep things simple. To be extremely precise though, we need to use Einstein's theory of general relativity to consider the curvature of spacetime. We use the mass of an object to calculate its effects on spacetime to find out the geometry, and this geometry is what the particles will be interacting with. It has more steps and it's much more complex, but it's also much more accurate and can explain more observable phenomena. Newton's law and Einstein's theory are both under classical physics and have not been reconciliated with quantum mechanics just yet. So let's get into each of them and see exactly what they state and what they attempt to describe. Newton's law of universal gravitation states that every particle attracts every other particle in the universe with an instantaneous force determined by their mass and their distance. In this description, gravity is a force. Space and time are separate things, both absolute and unaffected by the matter in it. There's no concept of gravitational waves, and no speed of light limit for the effects of gravity. This doesn't make Newton wrong because he didn't even attempt to answer those questions when he came up with his law. It just makes his law incomplete to explain everything we can observe. But what his law attempted to explain, which is how gravity works based on mass and distance, is still accurate and used today after centuries since its conception. Einstein's theory of general relativity, on the other hand, is much more than just about gravity. In 1905, Einstein came up with his theory of special relativity that states two things. One is that the laws of physics are invariant, in other words identical, in all inertial systems, which are non-accelerating frames of reference, that are either at rest or moving at a constant velocity. The second statement is that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. In other words, light in a vacuum doesn't behave like cars on the highway, where a car moving 10 kilometers per hour faster than you only seems to overtake you at 10 kilometers per hour. Regardless if you're moving head-on towards the light source in the same direction as it or perpendicular to it, it will always be moving at the speed of light. This means that if you're moving at half the speed of light and light catches up to you, it won't look half as fast like cars on the highway. It'll still be moving at the speed of light in relation to you. Another way of analyzing this is that it's not possible to make the speed of light appear to change by moving towards or away from the light source. In short, special relativity explains relativistic effects like two observers perceiving the where and when events differently based on their frame of reference. This theory of special relativity is what led Einstein to work on an entire decade on unifying our three dimensions with the one time dimension to form one four-dimensional continuum called spacetime. This was the basis for his theory of general relativity, which he published 10 years later in 1915. Before we get to gravity, let's go through the other phenomena that this theory explains and predicted. One of the first was the orbit of Mercury that couldn't be fully explained using just Newton's law. Then there's time dilation that explains how time is relative based on your velocity, where faster speeds equals slower time. Then there's gravitational lensing, which explains how distorted spacetime from gravity can change the path of light. Then there's the time delay of light, which explains how light can take longer to get to a destination if its normal straight path becomes curved by the effects of gravity on spacetime. Then there's gravitational waves that are produced by changes in mass and cause ripples that move at the speed of light, just like throwing a rock in a pond. Then there's the prediction of a non-static universe, and then the redshift of light, which you can go learn more about in my video on what light is. Now, in this theory, gravity is not a force, but rather a property of spacetime itself, which is also why gravity is not in the name. It explains how massive objects curve spacetime around them, which in turn interacts with the particles existing in it. This curvature of spacetime and its effects on the particles is what gravity is according to general relativity. So with Einstein's theory of general relativity, time is relative to the velocity of the observer, the effects of gravity propagates as a wave at the speed of light, which means there's no action at a distance like Newton thought, and gravitational fields from massive objects change the geometry of spacetime. This curved geometry is what the particles interact with, including light, which has no mass. In other words, matter tells spacetime how to curve, and spacetime tells matter how to move. Even after over 100 years, general relativity still hasn't been falsified by anything, and it stood up to literally countless attempts to falsify it. More recently, it was proven correct again as we took the first real picture of a black hole, which I made a video on if you want to check it out. Laws are usually simpler in their approach because they only explain how an observed phenomenon works, like dropping something always falls to the ground. It's possible that eventually we find additional information and adapt laws as well, like dropping something always falls to the ground unless this and that. Since theories attempt to explain why something happens, it's much more open-ended by nature, so they're harder to get right and are more likely to be the ones needing to be changed as we gain more knowledge about specific phenomena. One thing is certain though, both Newton and Einstein still don't explain gravity fully. We know this because they both reside in classical physics, and our knowledge of gravity breaks down in quantum mechanics as we get down to the atomic and subatomic scales. They also both rely on a gravitational constant called big G that we know is accurate to at least 4 decimal places, but it's not yet explained. All the other fundamental forces are described in quantum mechanics, so it's just gravity that's left to be reconciled. Until that happens, we know we're missing some information. What we're hoping for is that at some point we can unify quantum mechanics and general relativity under one theory of quantum gravity that will fill in the missing gaps to work at every scale and complete our understanding of the fundamentals of gravity. I want to say a special thank you to my first few patrons on Patreon that help support the channel: Tony W, Mr. K, and Dave S. I really appreciate your support. I'm also opening up my Discord server to the public to get a few people in there and get some discussions going. So if you're interested in coming for a chat, check the description for the invite link. This might be limited at some point, so get in quick if you're interested. If you'd like to learn more interesting science stuff, make sure to like, subscribe, and click the bell notification. If you'd like to help support the channel, you can visit my Patreon page for more information. For everything else, you can go to respectyourintellect.com and everything will be available there. Until next time, thanks for watching, and remember, respect your intellect.